Hello. I'd like to take a few moments to discuss the concept of solutions. And in particular, I want to emphasize the use of terms that are called tonicity terms. And then we'll discuss a little bit about how substances move from one solution area to another solution area. Okay? All right, first of all, solutions are a mixture. We're always talking about something that's being dissolved in something else. So we have a solute molecule that's being dissolved in a solvent molecule. Now, lucky for us, this semester, since we're dealing with biological systems, we're only ever going to deal with one solvent, and that's going to be water. Now, there are other solvents, but for biological systems, water is the key solvent used. Solute molecules, well, they come in a variety of forms. All different kinds of solute molecules. That might be what? Ions? They might be carbohydrates, proteins. They might even be some types of lipids. They could also be nucleotides, nucleic acids. So notice we're talking about any of the potential substances we might find in a cell could be a component of the solutes that are found in a particular solution. Now, one of the things we try to do, we try to compare solutions. We try to look at them and make comparisons between different solutions in different regions of the cell or on two sides of a membrane. And we use terms called tonicity terms to make this comparison. Now, tonicity terms are used to just compare the solute concentration of two solutions. Make sure you realize that it's always used in a comparative sense. If I say that something is hypertonic compared to something else, I'm saying it has more solute. If I say something is hypotonic compared to something else, it has less solute than the other thing. And if two solutions have the same amount of solute, we say that they are isotonic. Now remember, it's a comparative term. So if I came in one day and said, hey, I'm feeling hypertonic today, your first question should be, compared to what? It's always used in a comparative sense. So let's take a look at some solutions and let's see if we can do a few comparisons. All right, so take a moment to look at these different examples. 4 different solutions. Notice they all differ in terms of their percent water. They have amounts of water percent listed, percent water, the solvent. And they also have listed for you the percent solute concentration. So let's take a few of these and do a pairwise comparison and use those tonicity terms to make the comparisons. Solution A is hypotonic to solution B. Well, that's right. Notice solution A has less solute than solution B. So we'd say, yeah, that's a true statement. A is hypotonic to B. By the way, if I turned that around, I'd have to say that solution B is hypertonic compared to solution A. Notice, comparative sense. Solution C is hypertonic to solution A. Yep, that fits too. That's a true statement. Solution C has 30% solute, solution A 10%. So that's an appropriate comparison. Once again, if I flip that around, I could say that solution A is what? Hypotonic compared to solution C, right? Yes. How about another one? B is hypertonic to solution A. Well, I just mentioned that a moment ago, didn't I? Look at the numbers and see if it makes sense. Solution B has 20% solute, solution A 10% solute. So hypertonic is the appropriate term to use to compare B to A. And solution A is hypotonic to solution D. Yes, indeed it is. Solution A has 10%, solution D 20%. Solution A is the hypotonic solution in this comparison. And finally, solution D is isotonic to solution B. They both have the same concentration of solute. You want to practice using these terms. It'll become important that you're going to be able to utilize these terms to make these comparisons. And also, as you might expect, I'm going to ask questions in such a way that I use this terminology. You're going to want to know what it means. Now, in addition to knowing something about the way in which solutions differ in solute concentration, we want to consider how that might affect the diffusion of materials through a membrane. Remember, diffusion in general is just a passive movement of substances from a region of higher to a region of lower concentration. But now we want to take a look at the two components of a solution and consider how they might diffuse through a membrane. So, osmosis is the term used when we're talking about the diffusion of a solvent, in our case, what? Water, through a selectively permeable membrane, across a cell membrane, for example. Osmosis, water. Dialysis is the term that's used to talk about that simple diffusion process in regards to solute molecules. Solute molecules that might be moving through a membrane from regions of higher to lower concentration. Remember, in general, diffusion is something that has a tendency to occur from a region of higher to lower concentration. You don't want to think of it as being only in one direction. Remember, if a molecule can move from high to low across a membrane, it could also move from low to high. We just wouldn't expect it to be that common. We'd expect more molecules to move from the higher to the lower concentration region. And we're going to want to take a look at some examples of this in relation to what we might think of as a generalized cell membrane. So, for example, let's consider this circle to represent a simplified cell. Inside the cell, we're saying that there's 80% water and 20% solute. Outside of the cell, we're saying that there's 90% water and 10% solute. All right, well, first of all, let's use our tonicity terms. I could say that the extracellular solution is hypotonic compared to the intracellular solution. Or to turn it around, I could say that the intracellular solution is hypertonic to the extracellular solution. Remember, those terms are used just to compare the solute. All right, so now let's consider what should happen in relation to the movement, the diffusion of water, the solvent molecule, and what should happen if the solute molecule can also fit through the membrane and diffuse. First, let's consider osmosis. Notice I've used in this illustration two different sized arrows. A larger, bolder arrow and a smaller one. Think of those as representing differences in amount. So in this illustration, I'm trying to show that there would be more water moving into the cell than moving out of the cell. The way I could say that in terms is that there's a net intracellular osmosis. That means more water going in than coming out. Notice the arrows point in both directions. I want you to keep reminding yourself that if things can diffuse one way through a membrane, they can diffuse the other way through a membrane. In the simplest form of diffusion, we'd expect it to occur in both directions, but we would expect it to occur mostly from a higher region to a lower region. Notice the water's moving from a region of 90% concentration to a region of 80% concentration primarily. Let's flip over to the other side of the illustration and take a look at the dialysis. Now we're focused on the solute molecule. Once again, big arrow and a small arrow. Here I'm trying to represent the idea that I'd expect there to be more dialysis going out of the cell than dialysis into the cell. We would say in words that there's a net extracellular dialysis. You can see why that might be the case because what? The solute molecule is 20% inside, 10% outside. We'd expect it to move more from the 20 to the 10 than from the 10 to the 20. Remember simple diffusion. The tendency of substances to move from where there's more of them to where there's less of them. Doesn't mean they only move in that direction. All right, so take a moment to consider this illustration because what I want to do then is I want to give you a couple other illustrations and see if you can work with me to interpret those. In this particular one, we're seeing the same representation we had before. Make sure that the terms at the top of the slide make sense to you. Let me take a moment. You look at it and think about it. Think about what the words net intracellular and net extracellular mean. And you can see that that really applies primarily to that large arrow, the darker, bigger arrow. So what would we say? Oh, we have a net intracellular osmosis. How do I say that in words? More water moving in than moving out. We have a net extracellular dialysis. Again, in words, more solute molecules are moving out of the cell than are moving into the cell. Take a look at this difference. Give yourself a moment to consider the illustration. Notice some of the things that have changed. The key thing that I've changed in this illustration is what? I changed the concentrations. Notice that the outside environment still has 90% to 10%, but I've shifted the internal environment, haven't I? I've said, oh, what if I have a cell with 95% water, 5% solute? Take a moment. use those tonicity terms. See if you can use them correctly before I do. Compare the outside environment to the cell. Turn that around. Compare the cell to the outside environment. Let's see if you chose the right terms. If I'm comparing the outside environment to the cell's interior, I would say that the extracellular environment is hypertonic compared to the environment inside the cell. Remember, that means that the outside has more solute than the inside does. Excuse me. If I turn that around and compare the inside of the cell to the outside, I'd say that the intracellular solution is hypotonic compared to the extracellular solution. You can see how those terms are going to be used. You want to practice making use of them, though. Now take a look at my arrows. Once again, big arrow means more, little arrow means less. You can see that the water has a tendency to move more from the 95 to the 90. We would say what? A net extracellular osmosis. The dialysis situation, the solute is moving more from the 10% region to the 5% region. So we'd say what? A net intracellular dialysis. You're probably going to want to take a look at these illustrations a few times and keep practicing understanding or explaining how these terms are being used, and in particular, practice using the tonicity terms. Now, why is this, or how is this important to a cell? Well, water balance is vital for living things. Remember, we said that you as a living thing are primarily bags, compartmentalized aqueous solutions, right? Our membrane creates a region to try to regulate, in particular, water flow. So let's just consider water balance in relation to animal cells versus plant cells. You can see here that if I took an animal cell and placed it into a solution that was hypotonic compared to the cell would have a net influx of water. There would be a net intracellular osmosis, and the cell might actually swell enough that it bursts, lysis, or the cell might lyse. If it's a plant cell, the cell might take on so much water that it swells and becomes very tight and rigid, and that's when the cell is said to be turgid. And in most cases, that's how we try to keep our plants at home in pots. We try to keep them watered so that the plant remains rigid. If the plant's in an isotonic, or the animal cell's in an isotonic environment, we'd expect that water moving in and moving out is going to be about the same. Well, that means that the animal cell is going to be, in a sense, in its normal condition, its normal appearance. For plant cells, we find that the plant cell might be a little bit flaccid. That means a little bit weak. And when you stop watering your plants at home, as you know, initially you just see them begin to become somewhat softened, a little bit limp. Now, what happens if I place either one of these cells into a hypertonic environment? Remember, we're talking about the outside environment compared to the cell's internal environment. So if we place a cell into a solution that is hypertonic compared to the cell, we'd expect the animal cell to have a net loss of water over time, and we might expect to see the cell shrivel on itself, like a balloon deflating. So the term that's commonly used for the shriveling of the animal cell is, you might see that the cell is referred to as being crenated or experiencing crenation. And in the case of a plant cell, the plant cell will lose so much water that its cell membrane will pull in away from the cell wall. The cell will become very limp. If it was one of my house plants, I might say that my plant is wilted. And we'd say that the cell has plasmolysed, which means that the cell membrane, the plasma membrane, has split away from the cell wall. You can see that organisms would need to be very concerned about their water content if they're going to maintain themselves in the appropriate chemical conditions to maintain cell function, normal cell metabolism. So make sure you realize that these ideas of osmosis and dialysis are critical for cell correct function, life. Also, when you do end up taking a course in AMP, you're going to find out that you'll really focus on the details of how fluids move from one tissue to another, one cell to another, from the bloodstream into the tissues, from the tissues into the lymph system, and it becomes a very important concept to understand. You'll see that it influences a variety of topics when we talk about either single-celled organisms or multi-celled organisms. All right, so remember, we were talking about, in this discussion, solutions, but in particular we were talking about solutions in relation to this passive process called diffusion, the movement of substances from a higher to lower region. We say it's a passive process because it's a downhill, spontaneous process just due to the kinetic energy of the molecules themselves bouncing into each other. The diffusion of solvent molecules through a cell membrane we called osmosis, or the diffusion of water, right? The key solvent we deal with. And we said that the diffusion of solute molecules through a membrane was called dialysis. Both of these processes, very, very important for normal cell function. And in particular, since we are organisms based upon aqueous solutions, the movement, the regulation of movement of water is vitally important for a cell. Well, thanks very much. I hope you enjoyed this discussion. I look forward to talking to you next time.